So the title of this paper is Reasoning about Reasoning about Reasoning. So what does that mean? A probabilistic program language, so PPLs, probabilistic program languages, are powerful tools for modeling and solving Bayesian inference problems. A PPL has three essential features, namely sampling, conditioning, and querying. Here, sampling corresponds to making random choices, and conditioning amounts to imposing constraints, either hard constraints or soft constraints on samples. The sampling and conditioning together mean that a probabilistic program defines a conditional distribution. And finally, querying corresponds to applying Bayesian inference to infer the conditional distribution. So as an example, we can use these three essential features of a PPL to model an agent that wants to reason about its possible choices of actions and make a rational choice. So this agent samples from a prior distribution of actions, obtains the cost associated with that action, and uses conditioning to impose the constraint that the higher the cost is, the exponentially less likely the action will be chosen. In other words, the program is conditioned on the agent being rational and choosing a low-cost action. So having defined this agent model, we can let the agent initiate its reasoning of good actions by querying the action model. The result of this querying is a conditional distribution of actions. And the sampling this distribution yields a good action. In most PPLs, queries are a first-class language construct. In particular, it is possible to nest queries inside queries to express inference of inference, or in other words, reasoning about reasoning. So here's an example. Here we model an agent in a Markov decision process where the agent chooses an action at each step to transition from one state to another. We can still use basically the same action function to model this agent, except that it now takes a state as input. The MDP agent makes a sequence of actions and traverses a sequence of states. So to make rational choices, the agent must reason about the cumulative cost that will be incurred by choosing an action in a given state. To compute this cumulative cost, we first make a state transition. The new state is S2, and the cost associated with that transition is now in C2. The cumulative cost must also include those costs incurred by future transitions. So if the new state S2 is not a terminal state, the agent needs to pick a new action for the new state. The agent does so by querying the action function to infer a good action to take. It then recursively calls the cost function to compute the future cost that will be incurred by taking that action. So the action and cost functions here are mutually recursive, with the queries recursively nested, modeling how the agent reasons about its own reasoning in future states. We can instantiate this MDP encoding on the problem of 2D motion planning. Here we have a robot whose constraint is to navigate to the goal region using as few steps as possible and avoid the red obstacle. Applying Bayesian inference to this program then automatically searches for a distribution of motion plans that meet the constraint. From this MDP encoding arises an interesting program equivalence question. What if nested queries enclose not only the recursive call to action, but also the recursive call to cost? Will this change affect how the MDP agent functions? That is, are the two versions of this MDP program semantically equivalent? We experimented with these encodings in the PPL, and it seems like the two MDP agents can sample equally good trajectories. So perhaps these two programs are indeed equivalent. What makes this equivalence problem interesting is that these two programs have very different performance characteristics. The program on the right led to exponentially less running time of inference for the inference algorithm used in this experiment. So if we could formally substantiate this equivalence of these two programs, then it would be justified to use one of them as a semantics preserving optimization of the other. So in this work, we were guided by this goal of being able to reason equationally about the probabilistic programs that make use of nested queries and general recursion. And to achieve this goal, we need to establish sound, easy-to-use equational reasoning principles. And to establish such equational reasoning principles, we first need to pin down a precise semantics for nested queries. The challenge is that we found no existing PPL semantics fully accounts for the powerful combination of nested queries and general recursion. As a result, our first contribution in this work is to give meaning to a PPL with nested queries and a general recursion using an operational semantics. We then develop equational reasoning principles using a logical relations approach. And lastly, we demonstrate how to use the equational reasoning principles on applications of reasoning about reasoning. It has been studied before how to give meaning to a PPL using operational semantics, though nested queries are not considered. The idea there is to first define a deterministic operational semantics and then integrate the operational semantics over randomness to form the measure semantics. Here, randomness is over a so-called entropy space, and a reduction step is a 5-tuple. With a starting entropy sigma, the evaluation can take a step from E to E prime. The reduction step possibly consumes some entropy in sigma to draw a sample. The leftover entropy is sigma prime. The reduction step can also, it also induces a weight factor W. This W captures how the reduction step changes the probability of the current execution. In most reductions, sigma prime is the same as sigma. The only exception is when the redax is sampling from a built-in distribution. The starting entropy sigma is split, with one half producing the sampled value and the other half of the entropy providing entropy for subsequent evaluation. Most reductions produce a weight factor of 1, meaning that they do not change the probability of the current execution. And the only exception is when a redax is doing scoring. We require scores to be bounded by 1 to ensure that in the presence of non-terminating executions, model evidence always exists. After the small step operational semantics is in place, we can then define an evaluation function. The definition is by induction on the remaining allowable evaluation steps, and it applies the small step semantics. And finally, when the evaluation function is defined, we can integrate it over the entropy space to form the measure semantics of a program. The true meaning of a probabilistic program is then the limit of the step index measures when the allowable number of steps is taken to infinity. Nested queries add an important twist. To consider how to define the reduction rule for query. Query performs Bayesian inference. According to the Bayes theorem, Bayesian inference consists in normalizing a non-normalized measure into a proper distribution. The normalization factor is called the model evidence, which is an integral. We can obtain this model evidence by integrating all possible evaluations. So the reduction rule should normalize the weight by the model evidence of the program being queried. Because of this normalization, the small step operational semantics now invokes the measure semantics. But recall that previously, the measure semantics was defined only after the operational semantics came into existence. Consequently, we will have to define the small step operational semantics, the evaluation function, and the measure semantics all in a mutually recursive way. In particular, this means that the small step semantics needs to be step indexed too. Another subtlety of query is that the model evidence, which is the denominator here, may be 0. In this case, a 0 model evidence exception is raised. The true meaning of a program is the limit of its step indexed measures. And we are interested in two measures. One is the model evidence, and the other is the value measure. That is the unnormalized probability of a program terminating to a value in the measurable set of values. But before we can take these limits, we must make sure that these limits do exist. Previously, in the absence of nested queries, monotonicity of the measures was obvious because the integrand, that is, the evaluation function, was monotonic with respect to the step index. So the limits were guaranteed to exist. But in the presence of nested queries, normalization causes the evaluation function to be no longer monotonic. So the question is the measure semantics still monotonic and has well-defined limits? It turns out that we can still prove the monotonicity of the measure semantics, although it is necessarily a much more complicated undertaking because all definitions are now mutually recursive. Specifically, we show that the step indexed model evidence is monotonically non-increasing and the step indexed value measure is non-decreasing. Now with the measures being monotone, and by the monotone convergence theorem, we know the limits must exist. Now that we have pinned down a precise semantics for nested queries, our next goal is to enable equational reasoning. The gold standard of equivalence is contextual equivalence, and we take the standard approach of using a logical relations model to establish contextual equivalence. To define contextual equivalence, we first need a notion of distinguishable program behaviors. In our setting, distinguishable program behaviors are the measures programs induce. Given this notion of distinguishability, two terms E1 and E2 are contextually equivalent if respectively composing them with any well-typed program context C yields two indistinguishable programs. That is, these two composite programs, C of E1 and C of E2, have the same measure semantics. The discriminating power of contextual equivalence arises from this universal quantification over program contexts. But it also makes it difficult to prove contextual equivalence directly. Therefore, we want to define a logical relations model for the PPL and prove that two programs are contextually equivalent whenever they are logically related. The definition of this logical relations model is largely standard. It employs step indexing and bias orthogonality. We establish the so-called fundamental property of logical relations. That is, an open term is logically related to itself. We then prove soundness, that is, logical relatedness implies contextual equivalence. And the proofs of these key results are mechanized using the clock proof assistant. We are now in a position to prove equivalences. In the rest of this talk, we will focus on the intuition and the potential implications of the equivalences. And we defer to the paper for how to prove these equivalences using the logical relations. Our first example is a coordination game from game theory. This application is actually the first example that Stomler and Goodman use to illustrate the modeling power of recursively nested queries. Let's say we have two agents, Alice and Bob, and they want to meet up, but they have no way of contacting each other. However, they do know each other's preference about the possible two locations. We can model Alice and Bob using two mutually recursive functions that capture how they reason. So Alice reasons as follows. She samples a location from her prior preference, reasons which location Bob would probably go to, and conditions her choice on Bob's choosing the same location. And Bob does his reasoning in a similar way. The recursive calls are placed inside queries, expressing that the agents recursively reason about how the other agent reasons. Given that this application is the first example discussed in previous literature, it is only natural to assume that nested queries are semantically indispensable in modeling this coordination game. That is, if we get rid of the nested queries in this example, the resulting program would not do what the original program does. Yet our logical relations approach allows us to prove that these two coordination games are contextually equivalent, which means, surprisingly, that nested queries are semantically irrelevant in this example. But do nested queries really add no value here? This figure plots the running time of inference for the two implementations. The inference algorithm at work is discrete enumerative inference. The x-axis is the problem size, namely the depth of recursive reasoning, and the y-axis is the running time in milliseconds in logarithmic scale. And the contrast is apparent. The program without nested queries has exponential running time of inference. So what's going on here? Results of nested queries are deterministic. They are distributions, so it makes sense to memorize them. The PPL used in this experiment is WebPeople. It supports the memorization of query results. And that's why the program with nested queries scales much better. By contrast, the program without nested queries just does not afford a natural way to compartmentalize the program into smaller units for memorization. So although nested queries are semantically irrelevant in this example, they are still meaningful performance-wise. In our second example, we return to the MDP agents discussed earlier in this talk. We can verify the contextual equivalence of these two encodings using a logical relations approach. As an aside, neither encoding is equivalent to a version that does not use nested queries. We then compare their running times. The x-axis here is the size of the inference problem, namely the horizons of the MDPs. We see that under discrete enumerative inference, both programs have exponential running time, even when results of nested queries are already being memorized. But the interesting thing here is one program scales exponentially worse than the other, as different ways to nest queries result in solving different inference subproblems, which have different complexities. Being able to formally confirming such equivalences then justifies using one of the programs as a semantics preserving optimization of the other. And finally, we note that such equivalences can be generalized to sequential decision-making in multi-agent scenarios. And one application is playing games like tic-tac-toe. There is prior work that studies the semantics and equational theory of probabilistic programs. And this slide lists some of those most relevant to this paper. An important formalization decision we make is that the argument of scoring must be bounded by 1. And we inherit this restriction from prior work to ensure that model evidence always exists. One-bounded scoring, however, limits expressive power. In particular, a general statistical modeling of observed data requires unrestricted scoring. However, the kind of queries that motivate our study are about modeling rational choice-making of agents. And one-bounded scoring normally suffices for modeling goals and preferences of such agents. To conclude, we have defined a semantics for PPLs with nested queries and recursion, and we discovered that they have a rich equational theory. Nested queries are not only semantically challenging, but they also pose challenges to efficient implementation. Our work is a step towards understanding and clarifying the semantics and equational theory of nested queries. And we hope this work can provide incentives for future research aimed at studying efficient inference technologies for this powerful probabilistic programming construct. Thank you.